Hello, I'm Dongmoon from Seoul National University. In this talk, I'll present CryoWire, the wire-driven microarchitecture designs for cryogenic computing. This work was done with my fellow students and my advisor, Professor Jangwoo. As you know, when we operate the computers at room temperature, we suffer from the power wall and memory wall problems. To resolve these problems, cryogenic computing has emerged as a highly promising solution. Cryogenic computing means the computing at extremely low temperature, such as below 100 Kelvin. Let me explain two major benefits of cryogenic computing. The first benefit is the low leakage current. As the leakage current is almost eliminated at the low temperature, we can greatly reduce the device power consumption. The second benefit is the low wire resistivity. As the wire resistivity is linearly reduced with the temperature, so we can build much faster memory. With these benefits, cryogenic computing can resolve both power wall and memory wall problems. In this work, we target to build the faster processors by using the fast cryogenic wires, so-called CryoWire. To achieve the goal, we focused on the pipeline and on-chip network because their performance can be greatly improved with CryoWire. For example, wire delay occupies more than 50% for some pipeline stage delays. In the case of on-chip network, wire delay also occupies 50% in the delay of conventional mesh architecture. As the wire becomes 3 times faster at the cryogenic temperature, the pipeline and on-chip network will be greatly improved at 77 Kelvin. Therefore, we aim to build the fast pipeline and network using fast CryoWire. However, current pipeline and network are not fully optimized for CryoWire. For example, even with 3 times faster wires, previous cryogenic core design achieves only 15% higher clock frequency. In addition, naively operating the mesh network at 77 Kelvin also shows the marginal speedup. Therefore, we must ask two important questions to use CryoWire. Why cannot the current CPU design take the full potential of CryoWire? And what are the CryoWire optimal CPU designs? To answer these questions, we set 3 research goals. First, we target to build the architectural models for the cryogenic pipeline and networks. Second, we aim to find the design guidelines to fully utilize CryoWire. Finally, we target to propose the wire-driven cryogenic pipeline and network designs. Let me show our cryogenic pipeline and network models with the validation. This is the overview of our models targeting 77 Kelvin. First, pipeline model predicts the critical path delay of each pipeline stage. Next, the network model predicts the router frequency and wire link latency. Let me introduce our pipeline model. We build our pipeline model on the existing cryogenic processor model, so-called CC model. This is how CC model works. First, based on the target technology and voltage level, cryogenic MOSFET and wire models predict the MOSFET and wire characteristics. Then, using the prediction, the processor model estimates the critical path delay. However, CC model cannot accurately model the wire latency because a realistic floor plan is not considered. Also, the model cannot deeply analyze each pipeline stage because it only shows the longest critical path delay. To resolve these problems, we built floor-plan-aware wire model and a stage-wise path analysis. First, for the floor-plan-aware wire model, we first adapt the floor plan of Skylake and model the long wire latency with SPICE simulation. For hardware modules delay, we utilize design compiler. Next, For the stage-wise path analysis, we make design compiler separately analyze the delay of each pipeline stage. Therefore, our pipeline model can predict the critical path delay of each pipeline stage with realistic floor plan. Next, by using CC model, we build our cryogenic network model. The network model consists of the router model and the wire link model. First, for the router model, we enable CC model to take the router design. Therefore, our model can predict the critical path delay of cryogenic router. Second, for the wire link model, we extend Kekta Inuka to take the cryogenic MOSFET and wire characteristics. So, our model also predicts the wire link latency at 77 Kelvin. We validate our models with the measurement and simulation. For the pipeline and router models, we compare our prediction with the real measurement. The figure shows the validation setup. In this setup, we can separately cool down the processor and change the clock frequency of pipeline and router. For the wire link model, we compare our prediction with the SPICE simulation result. For simulation, we utilize an industry-validated MOSFET model and cryogenic wire property of Intel fabrication process. Let me show the validation result. First, the left figure shows the pipeline and router model results. Our prediction well matches with the measurement within the 2.8% error rate. On the other hand, the right figure shows the wire link validation result, which also well matches with the SPICE simulation result within 1.6% error rate. Therefore, we conclude that our pipeline and network models accurately predict the speed up at low temperatures. So far, we show how we build our pipeline and network models. From now on, we'll introduce our wire-driven microarchitectures for higher performance. We first introduce the wire-driven pipeline design. To find the guidelines for the pipeline at 77 Kelvin, we first introduce our baseline pipeline design. We use RISC-V Boom, which is the most complex out-of-order processor among the open-source processors. In our analysis, we focus on 13 representative stages shown in the figure. Note that we include 4 backend stages using long forwarding wire, such as execute bypass, data read from bypass, write back, and wake up from write back. From now on, we will call the stages as the backend forwarding stages. With the baseline design, we first analyze the critical path delay at the room temperature. For our analysis, we get 2 observations regarding the backend forwarding stages. First, the backend forwarding stages are the major performance bottleneck because they are unpipelinable stages. If we pipeline the backend forwarding stages, we cannot execute the dependent instruction in a single cycle. As a result, pipelining the forwarding stages much decreases IPC. Therefore, the forwarding stages cannot be further pipelined and limit the frequency scaling. Second, the backend forwarding stages have huge wire delay portion due to its long data forwarding wires. Their wire delay occupies more than 50% for their latency, which indicates their huge performance potential with the fast cryogenic wires. Next, we analyze the critical path delay at 77 Kelvin. In this analysis, we also get 2 observations. First, thanks to the reduced wire latency, we observe that the frequency bottlenecks moves to other pipelinable stages. This is because the latency of backend stages are greatly reduced more than others due to their huge wire delay portion at the room temperature. Therefore, the frequency bottlenecks moves to front-end stages. Second, we observe that we can greatly increase the clock frequency with the further front-end pipelining. Due to the huge delay difference between the front-end and back-end stages, we can greatly increase the clock frequency with the front-end pipelining. Note that Many front-end stages are pipelinable because there exists some front-end pipelining method with low IPC overhead. In summary, CryoWire enables more aggressive pipelining at 77 Kelvin. Therefore, we suggest applying front-end pipelining as our design guideline. Based on the design guideline, we propose CryoSP, the wire-driven super pipeline architecture. Our optimization starts from the cryocore, the state-of-the-art cryogenic processor of previous work. First, we apply front-end super pipelining following our analysis. We pipeline the branch prediction, cache access, decode and rename stages. As a result, we achieve 60% higher clock frequency than the room temperature processor. Second, we apply voltage scaling to the super pipelined processor. As the leakage power is almost eliminated at 77 Kelvin, we can further optimize the processor's voltage level. With the voltage scaling, we achieve 23% further frequency gain with the same power consumption. As a result, CryoSP achieves 97% higher clock frequency than those of the room temperature processor with the same total power consumption. Next, let me introduce CryoBus, the wire-driven cryogenic network design. To find the guidelines for the network at 77 Kelvin, we analyzed 4 major networks: mesh, flattened butterfly, concentrated mesh, and shared bus. For the comprehensive analysis, we assume the cryogenic optimized cache design, a twice faster cache design from the previous work. We first analyzed the network latency and S3 hit latency for the major networks. For the analysis, we observed that the shared bus becomes highly promising with CryoWire. First, when we focused on the network latency, the router-based network shows the low speedup because the router performance is bounded by the transistor. On the other hand, shared bus shows the 54% of huge speedup because it purely consists of the wire. The S3 hit latency shows the same trend at 77 Kelvin. The overall S3 latency of shared bus is reduced by 52%, unlike other router-based networks. In summary, shared bus becomes highly promising with CryoWire. Therefore, we suggest using shared bus as our first design guideline. Next, we analyze the bandwidth of shared bus at 77 Kelvin. From the analysis, we observed that we should improve the bus bandwidth to overcome the bus contention problem. First, thanks to the 3 times faster broadcasting with CryoWire, the shared bus at 77 Kelvin achieves 3 times higher bandwidth than that of the room temperature shared bus. However, even with the higher bus bandwidth, its bandwidth is insufficient to run the ordinary workloads. For example, cryogenic shared bus cannot run even cloud seed and spec workloads. In summary, the shared bus suffers from the bus contention problem at 77 Kelvin. Therefore, we suggest maximizing the bus bandwidth as our second design guideline. Following the 2 design guidelines, we propose CryoBus, the wire-driven scalable bus architecture. To make the shared bus scalable, we apply H3-based bus topology and the dynamic link connection. Starting from the naive shared bus, we first apply the H3-based bus topology to reduce the broadcasting distance. As a result, we can achieve 2.5 times higher broadcasting speed and bus bandwidth. Next, we apply dynamic link connection to enable H3-based bus topology. With the cross-link controller and switches, we can control the link connection at runtime. For the detailed dynamic link connection mechanism, please refer to our paper. With CryoBus, we achieve the higher speed, bandwidth, and power efficiency. The left figure shows the latency and bandwidth. The black line means the latency of mesh networks. First, CryoBus achieves 2.5 times higher bandwidth than 77 Kelvin shared bus, thanks to the shorter broadcasting distance. As a result, CryoBus overcomes the bus contention problem. In addition, CryoBus achieves 5 times lower latency than the mesh architecture. Next, right figure shows the total power consumption including the cooling cost. Compared to the room temperature mesh architecture, CryoBus consumes 2.3 times less power thanks to the eliminated static power. Compared to the mesh architecture at 77 Kelvin, CryoBus consumes twice less power due to the absence of the power-hungry routers. From now on, we evaluate our two wire-driven architectures. We evaluate the performance of CryoSP and CryoBus in the 64-core system. We compare our architectures with two baselines. First, for the room temperature baseline, we use Intel Skylake processor with mesh network and DDR4 DRAM. Second, for the cryogenic baseline, we use state-of-the-art cryogenic core, cache, and memory designs. We exclude the power evaluation as we already showed the power efficiency of our microarchitectures. We use 9 parsec workloads for the evaluation. For the spec workloads, please refer to our paper. Let me show the performance result. The graph shows the speed up, which is normalized to the performance of cryogenic baseline. Thanks to the fast cryogenic units, the cryogenic baseline shows 53% higher performance than the room temperature baseline. First, CryoSP improved the performance by 16% thanks to its higher clock frequency. Next, CryoBus achieves 2.1 times of speed up and up to 4.6 times on stream cluster thanks to 5 times lower latency and snooping protocol. As the stream cluster contains large number of barrier instructions, stream cluster highly benefits from snoop-based protocol. Finally, CryoSP with CryoBus achieves 2.5 times of speed up on average, up to 5.7 times on stream cluster. The speed up is even higher than the sum of speed up with CryoSP and CryoBus only, which indicates their synergistic impact. I will summarize my talk as follows. First, we develop and validate cryogenic pipeline and network models. Second, we propose two wire-driven cryogenic architectures, CryoSP and CryoBus. Finally, we show the potential of CryoWire. CryoWire achieves 3.8 times higher performance than the room temperature baseline. Compared to the cryogenic baseline, CryoWire achieves 2.5 times higher performance with a lower total power consumption. Thank you for listening, and please let me know if you have any questions.